Hello, Chem 111. This video is about trends in atomic and ionic radii. So I want to start by reminding us that when we look at the periodic table here, I've left off the F block. I just have the S, D, and P blocks. And as a reminder, when we talk about trends in the periodic table, we generally take the S block and the P block and we leave out the D block and kind of moosh them together into a rectangle like this that we call the representative elements. And as you'll learn in class, or you have learned in class, the atomic radius trend, it looks like this. So the atomic radius trend within the representative elements has the radius increasing from right to left, or you can think of it as decreasing left to right, and increasing down columns. So I like to encapsulate this actually just with a picture, which has a really big circle at this corner of the representative elements and a small circle there. That means the smallest corner is the upper right and the largest corner is the lower left. Okay. So using that trend, I can ask a question like, so question would be rank the following atoms in order of radius or size. And we use those two terms interchangeably. And so, for example, I could ask you about phosphorus, sulfur, and arsenic. And given the trend I wrote above, you can pause the video here and then come back when you'd like to see the answer. Okay, so if you're back, let's first of all identify where these are. I have phosphorus, arsenic, and sulfur right here. And I can see they're not all in the same column or they're not all in the same row. So can I say something about them? Well, I can say, for starters, that phosphorus and sulfur are in the same row, or period, as we call it. And because the trend is that radius increases from right to left, that means I would expect phosphorus to have a bigger radius than sulfur. If I look at phosphorus and arsenic, they are in the same column, which we call a group. And in that case, the trend is that the radius increases going down, so I would expect arsenic to be greater than phosphorus. And in this case, I can in fact rank them completely using the transitive property, which is my favorite property. So the final answer is that arsenic is bigger than phosphorus, which is bigger than sulfur. And that's how we do radii trend. And I'll just say here, sometimes you get cases where it's not completely obvious, but you can articulate the different reasons why you might pick one versus the other. All right, so now I want to talk a little bit about ionic radius. So in ionic radii, we can compare species that have something in common. So that have either the number of electrons or the number of protons in common. So here's an example. If I want to compare for instance, the chloride ion and the potassium ion. So I can't just use a trend for these two because they have charge on them. So the trend works for neutrals. The trend could work for ions that have the same charge, but one is positive, one's negative. So in fact, I need other information. So if I look at the periodic table up here, I can see that chlorine has 7 protons. So I'll just make a little table here. I'll make protons and electrons. So chlorine has 7 protons. So it started out, when it was a chlorine atom, it had 17 electrons, but now it has 18 because it's a negatively charged ion. Potassium, on the other hand, which is over here, has 19 protons. So it started out as a neutral atom with 19 electrons, but it has lost 1 electron. And so it has 18 electrons too. And so this is what allows us to compare these two species. They have the same number of electrons. And so to answer the question of how the radii compare, I think it's helpful to think about it. So think of an ionic or atomic sort of tug of war. And on one side, you have protons pulling inward. So the protons are pulling the electrons inward. The electrons, remember, make the size of the atom. So protons pulling inward cause the radius to shrink. That's what they're doing. And on the other side, you have electrons pulling outward. And they're pulling outward because they're repelled by each other, and so they'd like to have more space, right? So electrons pulling outward, and that effect causes the radius to grow. So you have these two competing effects. Protons pulling on the electrons want to make the radius smaller, and electrons repelling against each other want the radius to grow larger. So when you do a comparison like chloride and potassium, you have to see how those two things balance each other. So in this example, it's the number of electrons that are the same. So the number of electrons is the same. So the outward pull is the same. This is a simplification, but it works, so we're going to do it. So the outward pull is the same. So what's going to distinguish it is which one has the stronger inward pull. And so that inward pull is about the protons. So chloride has 17 protons pulling in. The potassium ion has 19 protons pulling in. So potassium has the stronger inward pull. Potassium has the stronger inward pull. That means it will be the smaller radius. And that means then that chloride has the larger radius. So if I were just going to write this like I did before, I would say that chloride is going to have a larger radius than potassium. Okay, so now I'll do another example for you to try. So example 2, rank the radii of O2 minus, Na plus, and F minus. All right, so you can stop the video and come back when you want to see the answer. Okay, so for my answer, I find it helpful to just make a little table where I have the number of protons and the number of electrons. So I go back up to my periodic table, scroll, and let's see where these folks are. I have oxygen here, fluorine here, and sodium here. So the number of protons for these guys is their atomic number. So we have 8, 9 and 11. Those are the number of protons. Now, oxygen started out with 8 electrons. It's added 2, so it has 10. Sodium started out with 11 electrons, took away 1, also has 10. Fluoride started out with 9, added only 1 because it's minus 1, also 10. So in this case, they have the same number of electrons again. So I would say the same outward pull. And the inward pull, who has the strongest inward pull? Sodium plus is the strongest inward pull, and O2 minus is the weakest inward pull. So the strongest inward pull will give you the smallest radius. So that will have the smallest radius. F minus will be in the middle, and O2 minus will be there. I looked up the values then just for fun. It turns out in terms of picometers, in fact, they are 98 picometers, 133 picometers, and 140. So we were right with our prediction. Let's do one more example. And for this one, let's do, it's going to be a little different, copper plus versus copper 2 plus. Okay, so the first thing to notice is that these are not in my representative elements. So in terms of the atomic radius trend, so copper, I'll just highlight, is here. It's in the D block. So in terms of my atomic radius trend, I really am not sure how that would fit, say, with other things in its row. But we don't actually use that trend to figure out these ionic radii. So let's go ahead and you can go ahead and try it and come back when you want to see the answer. All right, I forgot to check when I scrolled up. Its atomic number is 29. So number of protons, number of electrons. Both species have 29 protons. Copper plus has lost 1 electron. Copper 2 plus has lost 2 electrons. And in this case, the thing that's the same is the number of protons. So they have the same inward pull. So who has the stronger outward pull? The stronger outward pull is 28 electrons. That's better than 27 electrons. So stronger outward pull means a bigger radius. So my answer to this problem is that copper plus is greater than copper 2 plus.